Good morning, and thank you for joining us. I'm Mike Human. I am the principal analyst for storage at G2M Research. And thank you for joining our webinar today with Kioxia. Our subject is 4 ways multi-protocol can maximize flash value. We'll flip to the next slide. So just kind of walk through the overall webinar agenda. As you can see, I'll go through the ground rules really quickly. And then we'll have a couple of live surveys in with the material. We'll do audience Q&A and wrap up at the end. This is being recorded. We'll make the link to this recording available to everybody that registered. That'll go out probably on Thursday along with a PDF of the slide deck, so that you can all look at this, and or if you missed it, you can see it then. Next slide, Ro. So if you think about kind of flash protocols today, right, or flash in general, there's a lot of different flash protocols exist. I mean, obviously we're all familiar with NVMe. We're also probably familiar with SAS and SATA, which were the precursor to that. But even within that, there's a lot of other different protocols that get laid upon these different ones, whether it's things like ZNS or different block protocols or custom FTL. Those are just a few examples of all the different protocols that are out there. Obviously, the more protocols you have to support with a device, the harder it is, or the number of devices you might have to have, or different types of devices in your data center. And obviously the problem that creates is that redeploying those resources as workloads change becomes challenging. Then you also have to provision for spares, right? So, if you have something fail, now you have to have multiple devices you have to have spared. And then finally, maintaining performance as applications are moved. So if you think about moving from one type of flash device that your application is using to another, how does that impact performance, right? And all these things really complicate, things like service level agreements and other areas like that. So what we're going to talk about today is the solution to those issues. And let me introduce, go ahead to the next slide, Earl, if you could. So on with us from Kioxia is Earl Filhauer. Earl is a senior staff product manager at Kioxia. And with that, Earl, I'll let you take it away.
Thanks, Mike. Appreciate the intro. And thank you all for spending a little bit of your day today here with me. So let's, without further ado, today we're going to talk about how, by making flash software defined, you can increase its value over fixed function flash by providing multiple software defined protocols. We'll do a few Zoom surveys like Mike said, and we'll have time at the end for questions from the audience. So, you'll have a time to do that after the talk. So let's start by talking about fixed flash protocols, basically what's out there today. All storage today is basically accessed with the same protocols that were developed for hard drive technology way back in the last century. Flash memory wasn't even so much as an idea when these things were developed, right? When Kioxia invented flash memory and the first SSDs were deployed in servers, they used these same hard drive based protocols. Now, this gave really easy backward compatibility, but tying flash to these legacy protocols has some real downsides. And first and foremost, the way storage is built today, you're pretty much stuck with whatever protocol it was assigned with, whatever it was programmed with at the factory. Kind of a black box of software, and you can't go in as an application developer and modify it to suit your particular application's needs. Fixed function, well, it's fixed in time. You're also losing a lot of the potential value of flash when you do it this way. Flash is inherently digital and massively parallel. So many SSDs today can have tens or even hundreds of flash die, which can theoretically be accessed all at once, all in parallel. But if the protocol was built for hard drives, it's hard to make that happen. Where this really hurts is when you're talking about deploying flash at cloud scale. Applications which could benefit from unique ways of managing flash memory, they just don't have the power to do so. The flash memory advancements, they're held back by these fixed protocols that are available today. and that's leaving value on the table. The fixed flash protocol drive really does cause headaches at cloud scale in a lot of different ways. First of all, you're going to need to stock and equip servers with multiple different drive types. That's a sourcing challenge. You see, you have to get all of these different drive types available. And then the servers, once the flash is installed, you're pretty much stuck with whatever they've been provisioned with. And you lose the flexibility of reprovisioning a server to a different application, because a lot of times that different application is going to need a different type of flash infrastructure. So that really impacts your operational flexibility. You don't have this flexibility because the protocols that are baked into the drive are essentially black boxes coming from the factory. And on top of that, not only do you have to initially acquire these individual drives, but you have to predict your future needs for these different types of drives. If you choose wrong, you're wasting you're not only wasting money, but you're potentially missing opportunities. If you choose wrong and don't have enough of a particular type of drive, you may not be able to scale your application as fast as you'd like to. Now that can really, really cut into the TCO for your final cloud scale applications. Now, I'm not saying that fixed protocol flash is a bad thing in general. I mean, yes, it's revolutionized the data center, and lots of technologies, lots of web services today that we take for granted couldn't exist without it. But I am saying that you can do a lot better than fixed flash protocols. And you can use flash more efficiently and get more value from your flash by thinking differently about how you access it. Flash, with its digital and parallel nature, it's limited by this legacy hard drive interface. Even NVM Express, like Mike mentioned earlier, it still has some of these assumptions and limitations baked into the protocol. That hurts the overall TCO. The fixed protocol can't readily adapt. Heck, it can't adapt to changing workloads, period. I mean, it's fixed. And it's going to tie a server into the role that that server was deployed for initially, for all time. And when you have more than one application, which, heck, this is cloud scale we're talking about, there's always more than one application. When you have that multiple applications, the fixed protocol flash is going to make your supply chain a lot more complex. You're going to need to stock and predict future needs, have spares online for all of these different SKUs, all of these individual types of flash. At the base of it all, you know, the fixed protocol flash has this protocol baked into the factory, and it's essentially a black box. And as a user, you're powerless to adapt it. You're just stuck with what you've been given. There is a better way, though. And so I'd love to have Mike, if you could set up the quick survey here. And apologies to the late, great Louis Anderson, who was alive when I did this slide, so sorry. Really, I'd love to understand what your biggest challenge with Flash today is at your scale, whether it's getting the max value, redeploying properly, lack of customization. We'll give you a few seconds for there. Mike, is that going to pop up? Will I be able to advance, or should I wait for them?
You can go ahead and advance. People are already answering the questions, so I think everybody's seeing it.
All right. Thank you very much, Mike.
No problem.
Okay, guys, so you can answer in your own time. Let me continue. So what is the answer to this fixed protocol flash problem? Well, it's the same answer as in the rest of your data center. Make it software defined. Flash is digital by nature, and make the best use of it with software. Let's see how this new technology, software-enabled Flash, can make Flash software defined and make Flash more valuable to your application. Software-enabled Flash is a new way of thinking about how applications at the cloud scale use flash memory. It's based on and open source software-defined principles, and it's not shackled by the legacy hard drive type interfaces. It provides control of the flash at a low level, but not too low. It provides it directly into the application itself. It provides powerful methods for controlling I/O latency, data placement, isolation, and offload that allows the application to control its own I/O performance and I/O requirements. Basically, by making flash software defined, software-enabled flash maximizes the utility, the performance, maximizes the parallelism we talked about, and the overall value of flash for these large-scale applications. So I'll go over quickly the major features of this, because these features are what enable software-enabled flash to provide multi-protocol support for a single drive type. So software-enabled flash, this is a new hardware model coupled with a software stack that runs on the host server. This new flash hardware focuses only on the media, which are the flash die to people outside of the flash producers. It focuses on controlling the flash die, managing them, and it provides custom offload capabilities and provides a new interface, a different interface, an interface that was built for the digital flash nature to the host. Now, the host in turn is running a new software-defined stack, which understands this new interface and allows the flash to be managed completely under the control of the application. So instead of just leaving the drive to handle it, the application can now orchestrate and manage the protocol at the lowest level, the latency outcomes, the data placement, etc., within the drive for that one application. Now, you won't be running software-enabled flash on existing drives. This is new hardware. And you won't be running software-enabled flash everywhere on, say, a client, a laptop, a small-scale database. Existing interface is probably good enough. Where software-enabled flash is really focused at is for cloud scale, where you're looking to optimize hundreds and thousands of these devices at one time. More concretely, software-enabled flash gives 4 major categories of capability to these cloud scale applications, these large applications. It enables workload isolation, and that's going to keep applications running on the same server from interfering with each other, ensuring your SLAs, or making it easier to ensure your SLAs. It also provides latency control, dynamically managing the relative priorities of IOs to allow the application itself to define, prioritize real-time IO needs over, say, longer-term maintenance requirements. It simplifies software-enabled flash. It simplifies flash migration, making it easier to move from, say, TLC to QLC, or between vendors to get the maximum flash economics and the best flash economics as you go in advance. And it also supports flash maintenance control that helps helps implement these new protocols. And we'll show that in a little bit. Workload isolation. Software-enabled flash helps solve the workload isolation issues, like the noisy neighbor problem, as we like to call it. If you've ever lived in a college dorm, you understand this very well, where a chatty process, a chatty neighbor, can affect and hurt the responsiveness of others on the same server. Somebody is interfering, or somebody is taking too much of the IO, etc. And software-enabled flash provides a unique way of controlling this problem and reducing it to almost nil. It does this through an application control data placement at the die level, physical flash die. Now this gives complete physical isolation. Application running in one virtual device cannot affect the flash running in another virtual device, plain and simple. And these can be reserved, again, by the application under software control. And on top of that, a more granular method, software-enabled flash supports software isolation, which we call quality of service domains. Now, this enables finer grain isolation and data placement control at the super block level, which is the super block is a stripe portion across a bunch of dies inside there. Think of it like a RAID stripe. And we call these quality service domains. And with the combination of the hardware and software isolation and the placement control, these are critical for preserving cloud scale application performance and meeting your SLAs. And software-enabled flash is really the only software-defined flash way to make this happen today. And for latency management, well, software-enabled flash was also built to enable I/O latency management for cloud scale, for hyperscale, for large-scale apps. The thing about latency is, yeah, everybody wants zero latency, but you can't have it. So you choose the best for your application. There's not one size fits all. Some applications work better with, say, the left-hand side where you have low latency with occasional outliers. Other applications are going to do much better with a much tighter distribution of latency outcomes. The problem is with existing flash today, you really don't get to choose between the two, but software-enabled flash does provide a method for enabling this level of fine-grained latency control. And it does this through advanced queuing methods implemented in the software-enabled flash hardware. Now we have priority queuing, round robin fair queuing. We also have die time weighted fair queuing, which allows enough knobs that applications and orchestration tools can customize the latency profile of an application, of multiple applications on one server at runtime as required. This tight latency control on that per workload basis can really make it easier to implement, say, multiple service classes with a single drive. And it relies on the hardware to ensure the fairness and timeliness of responses. So it's the best of both worlds. Migrating between flash technologies is often a challenging process, and software-enabled flash has thought about that as well. It was designed to ease this migration from the beginning between, say, technologies like TLC to QLC, but also between different flash vendors. And by making this faster and making it easier to move between flash generations, flash technologies, you can make it easier to deploy the latest flash advancements and let your data center take benefits from the improved flash economics of these flash advances faster. Finally, the background management and the orchestration. So on a regular SSD today, the background processes like garbage collection, like patrol reads, they can wreak havoc on your application's performance because they're happening at uncontrolled times. Software-enabled flash provides special hardware to do the work, the offload engines we talked about, but it places that hardware directly under your application control. This lets a cloud scale application, say, for example, put off lower priority tasks like this garbage collection until a downtime when the server load is lower. And that can help ensure things like main application response times. These special offload capabilities, they can also be used to perform some application logic data moves right inside the software-enabled flash drive itself. For things like, say, a database compaction, where normally you're taking a large file and skipping invalid portions and rewriting it into a new one. It's a it's a computationally simple, but it's a lot of I/O. Well, if you can do that in the drive, which you can with software-enabled flash in a single command, you don't need to use host memory or host CPU resources to make that happen. And that's very unique here. This is really focused on optimizing at all levels. And that's what software-enabled flash is. Now, finally, it's open source. The software stack that is running on the host, from the lowest level kernel device driver, which runs under Linux today, to the highest level software developer kit, it's all provided under open source software licensing terms. This means no more black boxes. This means that your application developers are free to open things up, look around, and optimize every little bit for their particular needs. Beyond just being open source too, we here at Kioxia, we're also working on creating a neutral open source software foundation to help shepherd the development of software-enabled flash and ensure its widespread community, availability, viability, and support multi-vendors. Now, that was a lot to take in about software-enabled flash, but let's see what happens when you take all the software-defined flexibility and you apply it to the problem of multi-protocol flash, or how do you make multi-protocol flash with software-enabled flash? In a nutshell, when you move that flash control into the application, it means that software-enabled flash is going to allow the creation of dynamic, under app control, optimized software-defined flash protocols. Applications can take full control of the isolation, the latency optimizations, the offload, the flash abstractions, and meld a single software-enabled flash device into something that's completely optimal for their particular workload and for other workloads on the fly without changing hardware. That's really the magic. So let's be a little more concrete. A few minutes ago, you saw this basic same diagram using fixed protocol flash with separate drive types in the storage there, and no way of optimally redeploying flash for new applications. So here we see the same kind of setup, but with software-enabled flash. Now, the multi-protocol capability allows the individual Ceph units to speak different protocols and reconfigure as needed without any hardware changes, without requiring different hardware. This results in a simplified supply chain and one type of drive that can change to meet your needs instead of having to worry about multiple drives for every individual need. Using the software-defined API, applications communicate with the software-enabled flash drive with whatever flash stack is best for their use case. A very simple software driver that runs inside the application itself. Things like a standard block device, make it look like an old hard drive, but really fast, zone namespace, customized flash translation lists, they're all possible. And as new applications appear or your workload balance changes, you can redeploy existing flash to a new protocol for a new application with new software. That's software defined. That's the power of software defined. Now, this is cool from an engineer. I love this, but from a business point of view, this can give you a better TCO as well, because you've got the simplified acquisition, easier deployment of cookie cutter identical drives. And not only that, but you're able to make better use of the flash, reuse it as your needs change. And there's, again, this is the power of software-enabled flash, the power of software-defined flash. So let's look at an example that we had our engineers run on a prototype system a little while ago. This is a single software-enabled flash device that is going to be running 3 different protocols at the same time. You can see zone 0, 1, and 2. And you can also note that there are some unallocated flash die. Again, this is pointing back to the placement control, the noisy neighbor control that we discussed earlier. In this demo, we have one zone that's dedicated to a mixed read and write workload. We have one zone that is running a customized flash layer optimized for read performance. We say, for example, say a streaming application, this would make sense. And we have one zone that's running a database application, a logging thing in zone namespace mode. So it's basically an append only. One piece of hardware, 3 different protocols, same time, under application, under software control. Now, this is a heat map of the actual running of the things. We have our block mode region. We have our customized FTL optimized for read performance. We have our customized zone namespace mode optimized for write performance. And you can see how A, things are isolated, and B, the different protocols are all running in parallel. Now, this demo, you're not particularly, most deployments are going to be running 3 different protocols at the same time, and they're definitely not going to have unused flash die. But what we're trying to show here is that you can do this, that the software-enabled flash can deliver multi-protocol under software control, and that there's nothing else out there that lets one drive behave 3 different ways at the same time. This for cloud scale, this really is an unprecedented opportunity to tune the flash for your specific application and maximize the value you can derive from it. And now I have our final survey. So I've talked about custom flash protocols. I'd love to get your input, whether you've looked at it, whether you've not looked at it, whether you actually are running them or want to try. So I believe Mike has popped that up for you, and I'll give you a couple seconds while we advance to the next slide. Wrapping things up. Multi-protocol using software-defined, software-enabled flash can really maximize flash value in 4 distinct ways. You can optimize your TCO with application-defined protocols to maximize this flash utilization and performance on a per application basis, as well as benefit from easier migration to newer flash technologies, better flash economics. On the operations side, that can be streamlined by allowing swift and easy redeployment of applications and servers without needing to redeploy flash resources. You don't need to have a different server to run a different type of application at optimal performance. You're able to redefine the flash in that server under application control. Now, this makes sourcing a lot easier because a single type of drive now can morph, can become any number of types of drives at runtime under application control. This makes it a lot easier for you to predict future needs, to keep stock on hand for spares, etc. To deploy flash, it becomes a lot easier with this single drive type. And finally, software-enabled flash is all about open source and the open source ecosystem. Developers are able to leverage the community. They're enabled to dig into the implementation and optimize it for their particular application, for their particular needs. And really the net there, no more black boxes. So with that, we have some more information available for you to get deeper, into software-enabled Flash. We've really just scratched the surface here. Our website, softwareenabledflash.com, provides a series of videos and white papers, infographics that go into a lot more detail about how software-enabled Flash performs its magic, how it can improve your TCO at the data center level, and how it can change the way you think about deploying Flash and using Flash in your applications. On top of that, because we are open source, our source code for the software-enabled Flash is available on our GitHub site under github.com/Kioxia America. And you can check that out to look at actual code samples today, or the existing code today. With that, I want to thank you all for your attendance and your time. And I hope this got you thinking a little bit about how multi-protocol Flash can make your data center work better, and how software-enabled Flash might be able to fit into your cloud scale workloads. And I think I can pass it to you, Mike, for Q&A.
Thank you very much, Earl. So we have a couple questions that have come in. The first one is, what are the ideal vertical markets for Kioxia SEF in the cloud scale environment?
So the verticals in the cloud, I would have assumed cloud would have been a vertical. These are
good point. Good point.
Again, because this is software defined, the key is that at very large scales, you're really trying to optimize every little bit of Flash, trying to get the maximum value. Whether the cloud scale is running, say, a storage application, a large block store, or say a logging service, software-enabled Flash is applicable to either one of those under software control, right? The same drive can perform optimally for either one of those workloads or other workloads as they come up. That's the key for software defined. Good question.
Yeah, okay. And the next question is, what are the cost or performance penalties for putting SEF, SDF inside a Flash device? Is it free? Is it something that impacts performance, or what have you seen from Kioxia's perspective?
So the key is, let me just pop back to a slide here. I can describe maybe a little bit, because this is more of a hardware question. Let me see. I'm more of a software guy, so I will do my best to answer that. The key here is, this is intended to make the optimal performance, and whether that's a latency or a bandwidth plays depending upon the software application. The controller itself is implementing not less, but a different type of protocol. Whereas, say, a Flash SSD today has to have firmware that's going to be doing things like garbage collection and control reads and all that good stuff behind the scenes. We've moved that into the application host, meaning leaving a lot more oomph on the controller, as it were, to do the magic of the hardware isolation, to do the magic of the special queuing modes on a per IO basis. So I'd say it's a wash to net positive, but I don't have particular numbers at this point in time, would be the best I can say. I hope that answers your question.
Yeah, so basically the controller is powerful enough to make these changes itself, and with the user application driving it, it's got the extra horsepower for that.
Well, it's not just that. It's more of a, you can optimize things by making things go faster, or you can optimize things by using a better algorithm. And I want to say the software-enabled Flash is all about using the better algorithm, because that's where the real gains are. Using a better way of using this Flash instead of the SSD trying to guess which IO is important. The application itself is defining and saying that this is my read for a database. I need it now. This is my background scrub do it whenever you want, low priority. That's really the key here, that the application can optimize its own algorithm for these things.
Very nice. The last question was, do you have any production deployments that you've seen, and kind of, what have you seen any particular areas where they've seen more value versus less for software-defined flash?
So software-defined flash today, we have not delivered or discussed any public deliveries yet, and I can't do that here. But the software-enabled flash itself, again, this is really all about cloud scale verticals. An individual database server is probably not the right spot for software-enabled flash. For a scale-out database with 500 nodes, I think software-enabled flash can make a significant TCO impact. So that's really what the target is. Again, this is cloud scale, this is hyperscale, this is large scale deployments.
Perfect. Well, with that, thank you very much, Earl. Just as a reminder, we are recording this session. The recordings for this will be made available to everybody that register for the session. We'll send you out an email link in the next couple of days. We'll have both the link to the recording as well as a PDF of the slide set. Thank you again, Earl. This has been a really good session, and thank you everybody for joining us from both myself and from Kioxia. And we look forward to you joining our next webinar.
Thanks all. Thanks, Mike.
Thank you.